Okay, sometime before. The reason we left this part 3, we keep on the classical side, very interesting. They put this part, the space base, on the part 3. But actually, you also cover at the last part. The reason is very simple. Because you only cover your analog space base only recently, right? So it should be good to cover this after you have already a good learning about your state space, your continuous.
结婚了，昨天结婚了。
relationship between the analog and digital and how to and regard to the exam and revision. Okay, first of all, I understand all of you already received the email to confirm the revision class for the young side will be on this Friday, right? So will be morning 9 to 11. There will also be another revision class at the SD side, but I don't think many of you want to go SD, CD for contribution and as a whole issue. Okay, and young poly side will be the same location because this is the only lecture series that got all of you. Okay, and the young poly side we only have about 40-50 students, so they just have a very small seminar room, which only holds about 50 students. Of course, in case some of you are not able to make on Friday, okay, just for instance, if you are not able to make it on Friday, but you still want to join the revision class, you still want more chance to go to SD side. But please, not everybody go to SD side, then the very small seminar room cannot host all of you. You alright? Because SD side is only for the space where we only have about 50 students. So they book seminar room, which is able to maximum 60 or 70 students. Okay? So just in case some of you, for example, you already have certain FIP project discussion with your provider, right? Or for example, you have some other tasks you want to do. You are not able to attend the classical size revision class on Friday. Okay, the class is scheduled on Friday morning, right? 9 to 11. Okay? And you encourage all of you to attend, but in case you are not able to attend that slot, there is some another opportunity. Okay, you want to SD side. But as I mentioned, SD side, the classroom side is small. Then they will put for the SD student first. Okay. But in case, worst case, okay, you really have something on, you cannot attend Friday, you still want to listen to the classical lecture, okay, to see whether there's certain thing, okay, so you want to take SD as another opportunity. And secondly, a lot of students ask about some of the exercise questions, right? So basically for those exercise questions are extra questions. From the feedback from the student, what I conduct lesson last year only conduct lesson at the SD side. I don't know the pattern for the young poly side, doing electronics and design course. For the SD side, last time we just followed whatever we did. But a lot of student feedback is very limited because in the last two side we only choose one set of tutorial, which usually we took at the last 2 weeks. So I already posted the tutorial question also. But the students think it's very actively find the tutorial question is not enough for them to exercise. So this is the reason for this year I put certain extra exercise questions, right? So for extra questions from week 1 to week 5, I already covered during the review session. Okay, so for the remaining ones, okay, first of all, actually, the week after that week, we usually cover one exercise question during the lessons, right? And if you notice, if you really practice on the exercise question, you will notice other questions are similar. But it's just different questions follow different focus on skills. It just encourage you to have more practice. But of course, if you still got doubt for those exercise questions, or if you want to know the answers to those exercise questions, okay, what we will do is because usually the last week we schedule for revision, but the good thing is this year we have this complimentary lecture for the class come over to Singapore side. So I don't need to do a formal revision. Because you will do the revision on Friday already. So what we will do is we will put next week, which we will still have lesson, but of course no identity. In case you got any doubt, no matter regarding the or regarding the exercise questions, or regarding to any other questions, related to the agent control part, okay, you have got to come and discuss. Okay, so that one we can make it as a more open, free and easy. And to benefit from more students, if you have certain questions, you have certain doubts on particular exercise questions, you want me to open, because definitely there is no time for us to go through all the exercise questions, and also I don't think we need, because we have covered one of the questions of each exercise. The rest actually basically are going to be it's just different number, different functions, although different steps. Sorry, following steps for you to certain practice. Another suggestion is, if you really want to know the so-called correct answer, it's better of me to give you correct answer and for you to give me your answer. Okay, then I can give you some remarks on your answers. I already received some of the so-called exercise question answers from students who are studying and over and okay, so if some of you want to check your answer whether it's correct or not, okay, you are welcome to send me your answer. Okay, then I can do similarly during the time during the literature review. Okay, I will mark from your answers. Then now we will share all those answers without your names. Okay, class. So for those who did not attend the exercise question, okay, that's okay. Or in case some of students really want to learn unlimited, you want to not only learn the correct answer, you also learn from your peers or your friends how they have done the exercise, where are some common questions or common things they made mistakes. Okay, so that can be a good learning. Okay, so regarding to the exercise question, okay, if there's a particular question you want me to explain, okay, first of all, you can send me email. Okay, if we got time next week, for example, I received an email, they say you want to focus on question 1 to 3. Okay, definitely next week we have 2 weeks, out of 2 hours. So within the 2 hours, we are able to cover this 1 to 3, we will cover this 1 to 3 to all of them. In case some of the students find certain exact questions here lost, need certain help. Okay, and if I did not receive any email, I did not receive any question you particular one to focus. Okay, then I will just be here, and for those who got questions, maybe you will try to exercise, you will do more revision in this week, especially after your Friday's revision class. For the revision class, I already invited Matthew to go through all the past year paper with solutions. And in the email, he said he will consider the planning his review, but whatever he will review, I cannot control. Because some of you feedback to me, you want to have a whole solution for the past year papers, right? Even though I have covered most of the questions one by one during the time when we cover that part in our lecture time. Some of the students still prefer to have a full set of the solution. And what I already suggest to some of you, I'm not sure whether you will go through the past year papers, but this is something I highlight to you. Okay. So anyway, for next week, okay, the arrangement is very free and easy for all of you. If you have questions, you want to come in the class. Okay, if you prefer to study by your own, it's fine with me. For those you want to have me to check whether your answer to this exercise question is correct or not, you can send me your answers. Okay, and after that, next week I will post all the student submission answers with my remarks. Okay, and Moodle. Okay, so for those you did not submit, you want to so-called correct answers. Actually, I don't want to so-called just publish the so-called correct answer. That is the easiest thing. I just need to use my mouse, drag and place, then click the OK button. That's all. But I I really want to encourage you to try, encourage you to exercise first. So I will only share the answers from you, okay, with my remarks. So that is can be also good to learn under the opportunity for all of you. Alright? Or any comments, any suggestions before we move on to this? Actually, for those questions, I'm not right to answer, but I think if you follow my lecture all the way, I guarantee you will get all the questions. And today's part is optional. Okay. Any other questions? As I said before last week, I can predict anything. Because last week I only seen the paper, so I'm not at the correct position to make anything. Alright? But what I say is what I predict previously or correct. Any other things before we move on? Okay, so today, first of all, we would like to review about the evaluations. And that part is something very important because if you see the last year paper, almost two-thirds of the questions come from these 2 weeks. My understanding, Dr. Matthew is intended to cover all. Okay, because he also mentioned to me, he said a lot of students have difficulty with the increased equation or so forth, which is your analog part. So most likely he will have cover both. I think he will cover on behalf of Professor Henry. Even though Henry is not coming, only Dr. Matthew is coming. So any question not only related to vision control. Okay, even though at the Glasgow side, this Dr. Matthew is the one basically in charge of the digital control part. But since it's a common module, it's the same module, so we can also answer you to review everything, okay, related to this module. So including the animal part. Okay? But I believe he's the person to set the exam question for the digital part. And Dr. Henry is the person to set the question for the animal part. But they work very closely. So I think you should be able to address all your questions regarding the end part. Any others? Okay, anyway, if you still have more questions, you can ask me next week. Okay, so first of all, last 2 weeks, we spent our 2 weeks time to cover the evaluations. And evaluation basically is to find out the equivalent control function. Okay, in the teacher domain from your computer domain. So we have gone through certain different approaches. I hope all of you, first of all, you understand how to carry on each approach. And secondly, you should understand what is the limitation of each approach and what are the focus of each approach. You should also understand the certain comparison among those different approaches. Of course, as I mentioned, usually the exam is very simple, you are only asking for the first one. Okay, but as a good engineer student, I hope you are not only able to carry on how to apply one or two approaches to do the analog to digital equivalent conversion, but you can also address, understand the difference, the focus, the limitations, and so forth. And at least there is one thing I want you, all of you, to understand beyond the exam is, even though we mention this one as an equivalent, but they are never equal. See, always about difference between your analog and digital, unless your sampling time is extremely short. Okay, no matter which method you adopt, no matter whether you are using the numeric approximation, no matter you are using the zero order hole and sample equivalence, so on and so forth, or the zero and the hole replacement, no matter which method you are using, they have their own limitations. They will never get exactly the same as your analog function. It's just equivalent at certain steps. Okay? Even though these things may not be exam, but it's some very, very critical information for me to deliver to the student. Because later, if you go for any industry now, you are going to apply the control. most likely you will put the modeling in your continuous domain based on your physics, based on your engineer study, you will get the transfer functions. After you get the transfer function, the differential equation, then later you are going to design the controller. After you design the controller, a lot of time, especially when previously you don't have a fast enough CPU and memory, then you will notice there always have a difference from your controller and your design one. The main reason is not because there are certain gap between the schematic design and your practical. One first thing that you consider is the difference between the analog and digital. Because most of the time, especially nowadays, you design a microcontroller to control a mobile device, or you design a controller for the aircraft or for the local engine, or those things. Basically, at the end, you are implementing a digital controller. And if you never aware the difference between the analog and digital, then a lot of things you assume to be the same, but actually do not. And those differences may make error, and those errors may make certain accident, may make certain things break down, may make something out of function, and so forth. So this is the reason through the whole module, actually if you now think back, what we have covered in the past 10 weeks. Basically, we have introduced the difference between analog and digital, and how to cover analog and digital. And I keep emphasizing there's always some difference between analog and digital conversion because of the discretization, because of the quantization. Okay, so basically in the last 2 weeks, we have covered the numeric approximation, we have covered the zero and the false replacement to look for the equivalence. We also have covered the zero order hole and the center equivalence. So for the numeric approximation, basically we have covered 3 parts, right? One is the forward, one is the backward, one is the trapezoidal, right? And for the trapezoidal, we got different names. Sometimes we name as the casting, because casting is the person with a good contribution. And they also got another name for the bilinear, because they look into the linear line in between the 2 points. So basically, the step is not difficult, it's quite straightforward, because in your transfer function, you have an S operator, right? So S function basically is a differentiation, right? So basically, you are going to use the Z function to replace the S. And for different methods, forward, backward, and trapezoidal, you just have a different Z function to replace the S operator. So if you ask me what are the step-by-step solutions, which is simple. First of all, you have to remember. If you cannot derive, if you prefer to remember, you remember what is the S operator corresponding to a function Z. So in the forward method, Z minus 1 divided by T. In the backward method, Z minus 1 divided by Z. In the trapezoidal, 2 divided by Z multiplied with Z minus 1 divided by Z plus 1. So these functions are not so difficult to remember, right? So as long as you remember this one, if you look at the question, they ask you which method. Ask you forward, ask you backward, ask the trapezoidal, then you just use corresponding Z function to replace your S operator. After done that, what you need to do, you may want to check, for example, the stability, whether they are still stable. Because for the backward casting method or the trapezoidal one, this two, if your S function is stable, you can guarantee your function will be stable. For forward, even your S function is stable, after you convert to the digital function, you may not necessarily to resolve the stability. The reason is simple because you see the red color one is the stable region in your continuous domain. But the stable region in your continuous domain, which is a negative plane, will map into the plane on the left side of positive 1. Some are still within your stable region, which is the unit circle, some will be outside. Okay? So first of all, for the forward method, the stability from continuous domain to a digital domain is not preserved. Okay, similarly, for the backward, there's still another thing we want to pay attention. If your continuous domain, if your S domain function is stable, of course, after you use the backward method, you will still be stable, right? Because your stable region will map into this graph, this red color one, and it's inside the unit circle. But still, one more thing you need to consider. What happens if a transfer function in your S domain actually is not stable? It's unstable. If it's unstable, it will be something in white. Alright? For the forward, as long as you are unstable, the white color one, of course, will always be unstable in your digital domain, in your Z domain, right? But now for the backward method, if it's unstable, some are maintained unstable outside the unit circle, but some are inside the unit circle. So which means if you use the backward method, some transfer function which is unstable in your S domain, your continuous domain, will fall into your unit circle which is stable region in your Z domain. So this is something you will also want to pay attention to. Okay? And the best matching among the three, if you only look at the stability region, the best matching should be the Custins method of the trapezoidal one. Okay? But they still have a certain distortions. So this is the reason after we introduce the tree method for the Custins method or for the bi-index method, we particularly introduce a so-called pre-mapping method. Because there's certain distortion, we want to pre-map to maintain certain features, okay, at certain critical frequency. So for this one, the first key item is the pre-mapping is not for all. It's only pre-map for a particular critical frequency. If the performance at that frequency is very critical, I want to reserve, I want to maintain the performance at that critical frequency, so I will put that frequency at a particular function. So how can we pre-map according to that critical frequency? First of all, you may want to revise your transfer function rather than HS. You particularly consider your critical frequency. Here is your omega. So I will rewrite my transfer function in the form of S divided by omega, which omega is your critical frequency. In the example, if you still remember our critical frequency is 3 million per second, then this one you put as S divided by 3. Okay? And then later on, we need to do certain pre-mapping. If your sampling time is fast enough, or if your capital T is small enough, you will notice, if this one is small enough, you will notice your, if let me see, your capital T is very, very small. Mathematically, if this one very, very small, your tangent angle should be the same as your radian, right? If your T is small enough, your omega 1 T divided by 2 tangent should be almost equivalent to omega 1 T divided by 2. Then you multiply with 2 divided by T, what you get? Okay, so if your T is small enough, if your sampling is fast enough, then you don't need to worry about the digitization, you don't need to worry about the distortion due to the discrimination, because your T is small. And mathematically, your omega 1 will be the same as your A. You may only have to do the pre-mapping is, if this T is not that small enough, then your A is not the same as omega. If the A is not the same as omega, then in order to reserve the critical response at the critical frequency, I'm going to replace the omega by A. So I'm going to replace A, for example, in the example question, the A is 3.149, which is not 3, right? So we use the 3.149 to replace the position at 3. Then we get a new function. So now you see the HTZ become a new function. It's not the same function, it's pre-mapped function. But later, for the S to Z transform, you still just apply the same thing as a trapezoidal. Just use 2 over T multiply with Z minus 1 divided by Z plus 1 to replace the S. But before you apply this conversion, before you use this Z function to replace your S, you need to convert, you need to wrap your HS, right, into a new function, which is HP. Okay, you need to wrap your HS to your HP. Okay. And today I hope you understand the reason why and when you need to do the pre-mapping. You only need to do the pre-mapping, or your pre-mapping will only make difference if your A is not the same as yours, right? If your A is the same as your omega, then your pre-mapping is back to yourself. Does not change anything. Now, what is the condition for your A to be omega? Mathematically, it's only when your T is small, right? If your T is very small, and that one, it can happen. For example, nowadays, if you use a very good CPU, how much is the CPU at your home laptop? I believe it's about 1 gigahertz or 2 gigahertz, even you have a dual core or quantum core, right? So if let me see, you take 1 gigahertz. 1 gigahertz, that means your T is what? 1 gigahertz, T is what? 10 power minus what? 9. So if your T is 10 power minus 9, then is it very small? It's small, right? Even you may consider, but it also depends on how much is the frequency you are consider. If your frequency consider your omega is 3, your 3 multiplied with 10 power minus 9, very small. Then you don't get to do any frequency. But if you consider about high frequency, if your low pass filter, the bandwidth is covered also 1 gigahertz. Then your 1 gigahertz multiplied with your CPU 1 gigahertz, then your omega multiplied with your T, what you get? You get 3.1. Then it's not that small. Then you will not be able to know, right? Is that right? So this is something you need to know. The reason why they use the pre-mapping. And why to use the technique to use this one to do the pre-mapping. And last week we talked about the other two methods. One is the zero pole matching. And that one is based on the S-plane mapping to the Z-plane, or the Z-plane mapping to the S-plane. And one of the key transform function is Z equal to E power of S. And for this one is, because it puts a mapping between your S map to your Z map, right? And this conversion is according to this function. So you will focus on your pole and zero analysis. So first of all, you should convert your transfer function into a zero and a pole format. Once you get the poles and zeros in your S function, then you are going to find the equivalent Z function based on the zero and the pole. So if you are able to write the transfer function in the zero and the poles, so what are the factors you are looking for? You are looking for poles, you are looking for zeros, and what? And what? For any transfer function, if you rewrite in the zero and pole format, what are the three factors? Of course, zeros, right? Of course, poles, right? Then, still one more thing. It applies to both your digital and analog control. If you rewrite if let me see your transfer function GS is write as S minus S1001, S20, and so forth. And the pole if you have N zeros and N poles. So besides you understand, you need to know the zeros, you need to know the poles, anything you need to know to define the function. What do you know to define the function? Still one item, what it is? K, right? The gain, right? So you still have to define the gain. So basically for the pole and zero matching is, I'm going to map corresponding GZ I map So the idea basically, you have zeros, I can convert through the mapping, I can find so-called the equivalence position at the Z domain, at the Z space, right? So if you have a pole, if you have a zero on your S, I'm able to find the corresponding pole and zeros at the Z domain. So the first step, what I need to do, I need to convert the pole and zeros from the S to Z. And that one is not difficult. If you have a normal zero, you have normal poles, you just let me see, this is your zero at your S. Then this one will convert to the corresponding zero at your zero domain, right? So you just substitute your S into E power ST, then you get your zero at your Z domain. Similarly, the pole you get the pole. You get a pole on your S domain, you substitute into the function, then you get the corresponding pole at your Z domain. Hey, why it appear like first time you get it? I think this is a bit upper. Okay, the so-called I is any. Okay, let me see, I have first pole, second pole, third pole, right? So you can convert to the first, second, third poles, right? Okay. I is just an index, okay? Because you may not only have one pole, you may not only have one zero, right? But corresponding, you are going to know. But, so this is the magic function. Besides this magic function, there's still one critical thing you want to pay attention for the zero and pole magic. Because theoretically, the number of poles and the number of tables are supposed to be the same. Right? If they're not the same, in your continuous control, you have all these kinds of order 1, order 2, and order 3. Right? But theoretically, we want the zero and poles to be the same. If you got more poles, if you got more poles than the number of zeros, then we can see actually there's some hidden zeros. And those hidden zeros, based on the definition of the zero, zero is when your S equal to certain value, then your certain function becomes zero, right? So if let me see your poles, you got more number of poles than the number of zeros, means your below side, your order is higher, which means you have a hidden zeros when your S approach to infinite. Okay, when your S approach to infinite. So if your S goes to infinite, this one will become 0. How many number of zeros you are less? You're having less than the number of poles. Then you can see you have how many number of hidden zeros in your function. And after class, some of students come back to me to see still a little bit confusing is whether your infinite is positive infinite or negative infinite. Okay, first of all, mathematically, negative infinite and positive infinite is their event percentage because usually number is always okay, based on certain mathematicians' definition. But if you really want to insist, to make your understanding simpler, is what we are talking about for the transfer function, basically we are talking about the stable regions, right? When you talk about the stable region, it means your S, your poles, your zeros are on the negative side. Okay? So to make you understand easier, you can just think, okay, you so-called go to the negative infinite. Because example, for you to mapping, you are easier to understand the one map. Your E power SE, data you're going to map with the minus 1. Okay, because a lot of students very difficult to understand, hey, if S go infinite, it's go to infinite. The result should go infinite, it means nothing, right? Actually, they have a so-called fixed number. Okay. So for those poles, for those zeros and the infinite. For 0 and infinite, the one can map with a special point which is z equal to -1. And whether you are going to have the same number of 0 to poles, independent whether you have any delay in consideration. If in your exam there is no sentence mentioned about you have to consider 1 delay, 2 delay, and so forth, then you should take the number of poles to be the same as number of zeros. Okay? If there is a one sentence to say there is 1 delay in consideration, then you can remove 1 z equal to -1 because you will take z equal to infinite. Once so-called z equal to infinite, then basically you can combine everything, right? Then you just keep the number of poles is 1 more than zeros. So basically for the zero and poles matching, 3 things we want to consider. First one, once you get the zero and poles in your S function, then use the e power st to convert the corresponding to a zero in your z domain. Secondly, you need to consider a special case where you have more number of poles than the number of zeros. It means you have a hidden zeros and infinite. Then you need to convert. If your S is infinite, then this one convert to your Z one. So this is a special consideration. So this is the first one, the second one. Then the third step, what you have to do? You need to calculate a corresponding gain. How to calculate the corresponding gain? Your gain has nothing to do with your stability. For the pole and zero analysis, basically you are talking about the transient response. You are talking about the stability. But the gain itself, the K itself, has nothing to do with your stability, right? Right? If you look at the transfer function based on the pole and zeros domain, whether you change the K can change the stability, you won't. Whether this one will change your changing time, you won't. Whether this one will change your settling time, your writing time, you won't. Right? But this one will be something important for particular functions. Once you are not only consider about the stability, once you are not only consider about the settling time, the transient response. Because, for example, for filter, you want to maintain the gain to be 0. The gain to be 1. Right? You want to maintain the gain to be 1. In the same magnitude. If yours is an amplifier, you want to enlarge or reduce the signal, then the gain will be function. So after you put the analog to digital conversion, you still want to maintain this function. For example, you want to maintain the gain to be the same. Then you have to do the gain calculation as the last step. So you have to calculate what is the gain in your digital. So here you have a digital gain. So what's your digital gain? So what you have to do? The gain only means something if you have certain frequency. Because as I mentioned, your analog to digital conversion will not cover the whole domain. So usually you will look at certain critical frequency to reserve the gain. So what you are going to do? If your critical frequency is 0, then when your S is equal to 0, corresponding Z is 1. So you want to reserve the gain in your continuous domain when your HS equal to 0, You calculate this, you have here. So a corresponding function, when your j equal to 1, you have this function again should be the same. And now you know all the 0, you know all the poles. You substitute j equal to 1, you calculate again. And you know this gain should be equal to this gain, so you got 1 equation with 1 and no which is in each. Then you're able to calculate again to satisfy this function. So by this means, you solve all the 3 vectors. You know the gain, you know the zeros, you know the poles. Then you can find out the zero and pole. And of course, your zero and pole matching not limited to real number. You also can be extended to a complex number. Okay, for complex number, I believe for all of you are not so difficult because in your exam, you are allowed to use your calculator, right? Right? It's allowed to use calculator? Yes, right? And remember to be a calculator which is able to calculate complex number. Unless you want to calculate the complex number by yourself, which is also something to know, right? I believe all of you have used a computer which calculate the complex number. So basically, if your S is a complex number, your E of SE is also a complex number, right? Right? But if you don't have a calculator, you can separate your complex number to a real part and the imaginary part, right? Then this time your real part will form your amplitude, which is R, and your imaginary part will compute or contribute to your phase vector. And let me also highlight one more time. For this one, we do the matching. Again, when you S equal to 0 and Z equal to 1, is suppose the maximum frequency matching. Okay? And last one we covered last week is the sample and hold equation. The sample and hold equivalence, we have the sampling to cover your analog to digital. Then we have the zero order hold to cover your digital back to analog. And this simple function, I believe all of you are not new, right? Is the first time you have seen this? Yes, sir. That means you answer from my lesson. You deserve to do your method at least 3 times. Not only once, at least 3 times, right? So this one, basically, you use your continuous method function divided by S. Then you look from the table. Then you can look from the table to cover your S function, your Laplace function, to your Z function. After that, multiply with 1 minus Z function. Okay? So this one, is this simple? It's simple. Because everybody knows how to use F divided by S, right? Alright? All of you know how to use from the table from the left to the right. As long as you can do, everybody can do, right? Maybe technically the only one thing you want to pay attention is they did not give you a transfer function you can find easily from the table. It's a combination, immediate combination. So what you may need to do, you may need to do right? You may need to convert H divided by S, which you cannot find from the table directly, break down into something as a linear combination, and each one is equal to 5. Okay? Then don't forget to multiply with your 1 minus 1. Okay, maybe we have a short break. After that, we are going to talk about the space. Basically, we will continue this one to find out the space